Yeah. So in this session, basically, as in the first session, you have touched with the mathematical foundations for machine learning. In extension to that, and keeping the things that we are going to like in next few days, we will be touching the topics in MLDL and GenAI. So we'll look into some of the loss functions and optimization algorithms which can be further used to enhance the performance of the models, though it may be a machine learning or maybe a deep learning model. Okay. So yeah, so this is the brief outline for this session. We'll discuss we'll start with the introduction. Thereafter, we'll see the regression analysis, then different types of loss functions, and lastly the optimization algorithms. So under which I'm going to discuss the gradient descent algorithm. Okay. So what exactly is a loss function? Uh, when we talk about the loss function in machine learning, is a function which is used to measure the performance of the model. When we say that the performance of the model can be measured in terms of how closely we have predicted with respect to the ground truth predictions. Okay, so it is something that is basically, yeah, it is something that is with respect to the ground truths or the correct labels that we have in our hand. So mostly we calculate these loss functions with respect to the supervised problem, supervised learning. Okay. So it is actually, it converts the difference between the predicted output and the actual output into a single numerical value, which is called as a loss or an error. So that error is basically the difference between the predicted and the actual value. Okay. So in general, like this is a representation of any random regression analysis model. Okay. We like if we plot these points in a two-dimensional feature space, say on this axis, actually we have x, this is our x-axis, and this is our y-axis. Okay. So this x is nothing but also called as an independent variable. This x is also called as an independent variable, and y is called as a dependent variable. The value or the change in the value of x is actually depending on the change in the value of y. No, I'm sorry. This change in y, like this dependent variable, the change in dependent variable is actually depending on the value of x. Okay, so we will see in upcoming slides. I have one example where we can see this. So actually, when we draw or when we plot these points in a two-dimensional feature space, and then we draw a line which is the best fit for all those points. So this line is also called as a regression line. Okay, and now when we project this point, the actual value, and this would be my predicted value. Okay, whatever the value that I get on this line would be my predicted value. So the difference between this actual and this predicted is called as an error. Okay, so this, the inclusion of all random errors, error terms allows to fall either above the true regression line or below the regression line, where the error is greater than zero or could be less than zero. Okay. So there are two different terminologies. One is a loss function and another is a cost function. So what exactly it is, it's like many times we use it interchangeably. Okay. So loss function is nothing but when we calculate an error. Okay, when we calculate an error for a single training example or a single training sample. Okay, so that time basically this like this loss function is considered, like we need to the function that the error that we measure or calculate, and the function which is used to calculate that error is nothing but your loss function. So this is denoted by loss in bracket yi comma y hat I. Yi is basically your actual value, and y hat is nothing but your predicted value. This is for one example for we will see that mean squared error is actually a loss function which is used to measure the loss in terms of the regression. So this is the L is basically denoted by y minus y hat whole square. Okay, whereas The cost function is basically, it is nothing but it measures the error over the entire training data set. Okay, so let's say that I have some 100 samples, and for all those 100 samples, like from I is equals to 1 to n, I'm taking the loss with respect to all values, all 100 samples. And when I'm taking their average, then that becomes my cost function. Okay, so it measures the error over the entire training data set, and it is typically the average of individual losses. Okay, so this individually, this is considered as one loss. However, for entire training data set, this is basically a cost function. Okay, so here in this case, this n is a number of training samples, this n is a number of training samples, and theta basically the parameters of the model. Okay, so this theta is again is very important, right, at this point. Okay, so because based on the values of different values of theta, uh, we may get the cost function, we may get the values of cost function, different values of cost function. And these parameters, like these model parameters, will be further used to minimize the cost function, because anyways this is an error. So our task is to identify, our task is to find out or fine tune our model so that these parameters are so precise that the cost function would be minimized, or it will generate the minimum value for the cost function. So the cost function represents the overall model performance. So this is how like we measure in regression analysis. Mostly there are multiple performance analysis metrics which are again used as a cost functions. So basically this ME, like mean squared error is one of the cost function, and mean absolute error is also another cost function. Okay, so like these are the goal of our learning, the goal of our training the model is to minimize this cost function depending on the different values of theta or different values of model parameters. Let us take one simple example to understand it more, like the how the regression analysis to be performed, and how to generate a cost function for the regression analysis. Okay, so let's say that I'm giving with some training instances, training samples. Say I1 to IM are the samples provided to me in my data set, and these are some of the input features. Okay, x1, x2, x3, so on up to xn are the input features. Okay, and to these features, at the output we have corresponding y values. Okay, so this output can be a discrete value, the output can be a contiguous value, and depending on the labels, basically depending on their nature, we may to decide whether it is a classification problem or it is a regression problem. Okay, so we say that when y1 is a discrete value, then it is basically a problem for classification, and when y is a contiguous value, like house of a price, a house of like price of a house, or share market analysis, in these terms, these actually are the contiguous values. So in that case we need to apply the regression analysis, and our model is basically, we have to train a model, we have to train a model which is going to predict this, which is going to predict the value of y. Okay, and depending on these input features. Okay, so, like there are different types of learning, different types of machine learning, under which supervised, unsupervised, semi-supervised learnings are there. So this is basically more of a problem for supervised learning. So for each input x, the desired output y is given. That means the labels are provided in the supervised learning. So here y is basically your label, and pre-classified training examples, like given x and y pairs, for any unseen value of x we have to find out the best label y. Okay, so that could be my objective, that could be the objective of my model. Okay, so in classification, when y is discrete, so we have to apply classification algorithms when y is discrete. So the examples for y is like whether it is masked or not masked, whether it is red or black. It can be a three-class classification problem. If I'm provided with the set of images, then it can be the y can be cat, dog, or horse. Okay, and in terms of like regression, the y is actually a contiguous contiguous value. Okay, The examples can be carpet area for the house, that is size of the house. It can be the like price of the house depending on the location. Okay, so here in this case, basically based on the size and location, we can predict the price of the house. The price of the house would be a label in this case and would be a contiguous value. So in this case, basically we need to apply the regression analysis. So in general, the classification is the process of categorizing a given set of data into classes, different classes. Like it can be two classes, it can be more than two classes. So in that case, it could be a multi-level classification or binary classification. This can be performed on both structured and unstructured data. Okay, so this classification can be performed on a structured data as well as on unstructured data, like a set of documents with given labels we can perform. This is considered as a unstructured data. Okay, this process starts with predicting the class of a given data points. The classes are often referred to as a target or label or categories. Okay, so this is how like we have to predict the line between between two different classes. Okay, one simple example for classification is basically predicting the email is a spam email or a not spam email or a ham email. So like you are given with the collection of emails and determine the spam or non-spam email from it. Okay, so this is basically this classification problem is on unstructured data, where each email would be treated as one document, and there would be some like we need to identify some keywords. Based on those keywords we will have to train the model. Like if my model finds out that these the keywords present in a specific document, then would be treated as a like the labels would be assigned based on those keywords. Okay, so here the task is to learn the function which can classify and predict if the email is a spam or a non-spam. So we have, like here in this case we have two different functions, that is f1 and f2. Okay, and I can see that the f1 is a linear function whereas f2 is a non-linear function, and the performance of f2 is better compared to performance of f1. So this can be decided depending on the loss functions. Okay, so whether this f1 has generated good loss, like minimum loss, whether this f2 has generated minimum loss. Okay, so based on that we have to decide the function. There are different classification algorithms. I'm not going into details of it, just for the introduction purpose I'm just discussing it, because depending on this we will like few slides, few upcoming slides are there. So there we will discuss the loss function in terms of the linear regression model. There are different classification algorithms like SVM, decision tree, KNN, ANN are some of the classification algorithms which can be applied on this type of the data set. Okay. Then next is a regression. Okay, so what exactly regression? It is a technique for determining the statistical relationship between two or more variables. Okay, so like in regression analysis, when we have a single independent variable and single dependent variable, it is simply a problem of a linear regression model. Okay, and then when we have multiple independent variables and single dependent variables, then it is basically a multiple linear regression. And then depending on the type of depending on the number of dependent and independent variables, there are different regression analysis that we can perform. Okay, so this is a technique for determining statistical relationship between two or more variables where the change in a dependent variable is associated with and depends on the change in the more independent variables. Okay, so the change in the value of y is actually depending on the change in the value of x. Okay, a regression problem is used when the output variable is a real or contiguous value. Okay, so like such as salary or weight. Okay, so here actually we again need to plot the points in the two-dimensional feature space. This is basically a feature space where we are plotting this all these points, and then we need to find out the best regression line, the best line which is passing through these points. Okay, so there are different techniques to draw this line, and then to optimize it, again we need to find out the we need to work on some parameters. Okay, there are a few examples under the regression analysis. So sales of a product can be predicted by using the relationship between sales volume and amount of advertising. So in most of the industries, this regression analysis is being used to predict the sales of any particular product. For that sales, there are multiple factors. The factors can be the quality of the product. The factors can be the publicity, that is advertising of the product. So here in this case, like if I want to draw a simple linear regression model, so here in this case, the sales is basically depending on the amount of advertising. More the amount of advertising, more would be the sales that I consider. So this is like this can be considered as one of the regression analysis problem. The other thing is the performance of a student can be predicted by using the relationship between hours of study and the score in the exam. Okay, so we consider that we actually consider this that there is a direct relationship between the hours of study and the scores of a particular or the performance of a student in the exam. Okay, so again we draw here in this case the hours of study is actually a independent variable, and score is depending on that. That is y is basically the score. Next example can be the size of a child's vocabulary can be predicted using the relationship between the vocabulary size and child size. So it is like the the child when starts speaking, so that time the vocabulary size would be very low. However, when he turns down 5 or the 10 or 15, then automatically the vocabulary size will get increased. So these are some of the regression analysis examples. Okay, so obviously there are different regression techniques. As I said earlier, linear regression, when we have only two variables, that is one is independent variable x and another a variable dependent variable y. When we have multiple independent variable which are causing for the change in one single dependent variable, then it becomes a multiple regression. Okay, so let's take an one example. Through this example only, we will see how these loss functions can be calculated and how to optimize these loss functions. We also can use a simple Excel file, a simple Microsoft Excel, or a simple few lines of code can be written to find out the or to find out the best regression line. Okay, so this our task given to us is to predict the estimate the price of the house from the given data. Okay, so here data is given, that is the size of the house and the price of the house. Size of the house and the price of the house. I'm considering this size as small. I'm considering the size of this house is big. Okay, and these are the corresponding values. Okay, okay, so the problem given to me, like after training the model based on the size and the price, we need to basically predict the size of this house, which is actually which is actually having a medium size. Okay, compared to this one and this one. Okay, so obviously what I have to do, I have to draw a I have to plot these points on a 2D space, in the 2D space. On the y-axis, obviously, I want to predict the price of the house. So on the y-axis, I will draw this. I will plot this price of the house, and on the x-axis, I will have the size of the house. So here in this case, size of the house is actually treated as the independent variable. Okay. So what would be the price of the medium size house? So that is my objective. That is my objective. So what I will do, similarly, I will have other data, other samples. So what I will do, I will try to plot it. Okay, so this is like this is the size, and this would be the price of the house. I will draw a regression line. This would be considered like there are different methods to draw this. Okay, so initially I may choose a random value, any random value to draw this. how this can be drawn, it will get cleared very soon. Okay, uh, so I will draw a line, and here actually in this case, just for now, I will try to draw a line which is actually fitting to will be considered as a best line, and which will actually pass through all these points. Okay, so for now I'm drawing such line which is actually I'm trying to pass that line through all the points. Okay, through all these points. Okay, so here in this case, when we project this actually on the line, so this will give me the corresponding price of the house that I'm looking for. Okay, so for this house, like here in this case, 120K dollar would be the price of the house. Okay, so how to get this line? So that is one question. How we can get the line, and what are all parameters to decide this line? Okay, because obviously this line will have some equation, this line will have some equation. So let us say that this is the equation, that is y is equals to, so this is simple, y is equals to mx plus b would be the equation of the line. Okay, so here in this case, here for this case, basically we are considering that the equation of the line is basically w0 plus w1x plus epsilon. Okay, so here in this case, this w0 is nothing but the y-intercept. Okay, so obviously this line will not pass through the this line will not pass through 0. It will have some y-intercept. Okay, so we are treating this as also a bias. Okay, so here in this case, this w0 is basically the y-intercept, and this w1 is nothing but the slope. This w1 is nothing but the slope of the line. Okay, this is basically like I'm looking for this regression line which will be considered as the best line, and I'm trying to pass this line through all the points. Okay, so here in this case, basically if you see the difference between these two, like the actual value and the predicted value is very small. The distance between actual and predicted value is very small. That means this could be like, for this particular line, I'm assuming that the the cost function, like the cost function for this would be the minimum. Okay, or the loss would be minimum, average loss would be minimum here in this case. Okay, so obviously what I need to do, I need to find out the best fitted line. Okay, so to find out that, again I need to find out, I need to check which are all the parameters that can be considered. Okay, and how to get this line. I can again start with the random values of say w1 and w0 by choosing the random values, and then for each of those w0 and w1 value, we'll calculate the y hat for each of those samples, that is taking their differences, and for whichever the pair which generate a minimum value, the average minimum value, that w0 and w1 can be considered. However, there are other techniques. That is, one of the technique is least square method. Okay, so here in this case, actually this w0 is nothing but your y-intercept, and then this w1 is nothing but your slope. So slope is basically this change in y and with respect to change in x. Okay, so here in this case, what we are trying to do, this change in y is actually depending on the change in the value of x, and that gives me the slope. Okay, so this is basically we need to calculate here in this case. So when I calculate these two things, that is w0 and w1, then the other thing, so for now we assume this epsilon is nothing but the unexplained or random error component. Okay, so we assume that this epsilon is a negligible amount of error in our model while training our model. So when I get this w0 and w1, then I can predict the value of y for the corresponding value of x. Okay, so this could be the simple possible linear regression model. Okay, so here in this case, this is the base model for all statistical machine learning. Here in this case, x is one feature data variable, and y is the value we are trying to predict. So regression, the equation of the regression model can be y is equals to w0 plus w1x plus theta. Okay, so the linear regression is the simplest mathematical relationship between two variables x and y, which actually assumes that there is a linear relationship. We can have the nonlinear relationship as well, but here in this case, for the linear regression model, we are assuming that it has the linear relationship. So in a cause and effect relationship, the independent variable x is basically a cause for the change, or for the change in the value of y, that is also considered as a dependent variable, which is also a effect for this cause. Okay, so there is a least square linear regression method, which is actually used to get the value of these parameters. Okay, so this is a method for predicting the values of a dependent variable y based on the values of independent variable x. Okay, so the what we need to find out, we need to find out the value of m and b with the help of this y and x pairs. Okay, okay, so there are different types of loss functions. So once we get any such line, then what we need to find out, we need to find out, okay, I'm assuming that this is the best suitable line. So what I will do, I will try to find out the loss. I will try to find out the loss, average loss between these using like for these lines for different set of parameters. Okay, so like there are different types of loss functions. Amongst them, the very first function is a mean squared error. MSE is one of the most commonly used loss function for regression problems. It measures the average of squared differences between actual and predicted values. Okay, so this is actually the average of all these squared differences between the actual value and the predicted value. So why this we have taken the squared function? So there are some reasons behind it. It makes all errors positive. Obviously, when we are taking the square of it, the errors are converted into the positive scale. At the same time, for the large errors, it penalizes more. So if the prediction error like doubles, the MSC increases 4 times. Okay, so for large errors, it actually gives more penalty in such case. So the model strongly avoids the large mistakes. So if there are such errors, then that would be visible with the help of this squared loss, with the help of this mean squared error. It is a smooth and differentiable. It makes the function smooth and differentiable for at the minimum loss or at the minimum errors. For those small errors is actually smoothen well with respect to the other loss functions. Okay, the other one is the mean absolute error. Okay, so the mean absolute error is a regression loss that measures the average of absolute differences between the actual and predicted values. Okay, so here in this case, we have actually considered the absolute values. We have considered the absolute values of between the this absolute difference between the uh, actual value and the predicted value. So it tells us how far the predictions are from true value without squaring the errors. The benefits of using this MAE is basically it prevents the cancellation of positive and negative errors. It is robust for outliers. Okay, and for like if we have let's say that okay, like when to use which particular loss function is again depends on the type of the data that we are processing. If in my data set there are multiple outliers, then I may go ahead with the MAE instead of MSE. Okay, because this particular function is robust for such outliers. It treats all errors linearly, and it is actually, as we have seen that at near to zero, this particular loss function is not smooth and well. Okay, so these are the some reasons why actually one should not consider this. Okay, uh, there are other in regression analysis we have these two. In classification we have and again few more. So for classification we have loss functions such as binary cross entropy. So it is a loss function used for binary classification problem where the target variable has two classes, that is 0 and 1. Okay, so this loss function measures how well predicted probabilities match actual binary labels and is minimized during the training. So our task is basically to minimize this with respect to the actual value. Okay, and this binary cross entropy is again we calculate in terms of the log scales. Okay. Another is the categorical cross entropy. So it is a loss function used for multi-class classification problems. When we have more than two class labels present in a data set, then we go ahead with the categorical cross function, categorical cross entropy loss function. So where there are more than two classes, and then it is actually required. Again, we calculate it in the terms of what you say the log scale only. Okay. Okay. Okay, just a moment. Okay, I hope my screen is visible. Before actually moving ahead, I wanted to discuss this particular slide with you. Okay, so there are in regression analysis, there are different what I say types of loss functions. The choice of the loss function usually depends on the nature of data. So some loss function results in easier optimization problem than others. So there are many possible loss functions, out of which the one we have seen is a squared loss function, that is mean squared error. So as you can see here that for larger error, actually for larger loss, you can see that the actually it is generating more error with respect to the zero. Okay, for the small values of the error, you can see that it is smoothing well. Okay, however, this is very commonly used for regression, leads to an easy to solve optimization problem. The second one here is an absolute loss. Okay, so you can see that it grows slowly than the squared loss. Obviously the squared function is not applied over here, thus better suited when the data has some outliers. Okay, so when your data has some outliers, then then the better choice for the better choice would be of absolute would be the absolute loss or mean absolute loss. Okay, so here in this case you can see that inputs on which model makes large errors. So here at close to zero, this is not the smooth curve. Okay, so this is at even at close to zero, this is basically giving you the absolute values. So that's why like if you have small losses, if the cost function actually generating the small values, then one should choose the squared loss. Okay, then there are different types, other types, that is Huber loss. So it is basically nothing but the combination of the squared loss and the absolute loss. So close to zero, we are using again a squared loss. However, for the large value of loss, we are actually using the absolute loss. So this is a squared loss for small errors, say up to delta, and absolute loss for larger errors, good for all data with outliers. Okay. And there is one more loss. Again, the combination of it is basically the epsilon incentive loss. So this is also called as the Wapnick loss. Okay. Uh, so basically, this is basically a Wapnick loss. So again, it is an combination of the absolute loss, and I can say that the squared loss. Okay. So this zero for all this is zero for all small errors. So we assume that up to some epsilon values, we are assuming that even though there are some errors, we assume that the value for those errors are zero. And beyond some epsilon threshold, beyond that threshold, we assume that there would be some actual or absolute errors are there. Okay. So it can also use squared loss instead of absolute loss. So that we can have some combinations of this. However, the basic ones are the squared loss and the absolute loss. Okay. We just now covered these two things. That is the in classification, there are binary cross entropy and the categorical cross entropy. Okay. So far what we have seen is basically different loss functions. Okay, so how to decide these parameters, how to choose these parameters, there are different optimization algorithms. Okay, Okay, there are different optimization algorithms to decide those parameters. Okay, so here in this case, basically, gradient descent is one type of optimization algorithm. Actually, what I say, optimization means we are trying to optimize the cost function. We are trying to optimize or minimize the cost function for using some combination of parameters. Okay, so here in this case, in linear regression model, we have seen that the size of the house basically decides the price of the house. Okay, that means the y variable here is basically a price of the house. So the linear relationship between two variables, we have seen that can be represented with the help of this y is equals to mx plus c, mx plus b. So here y is a target and x is your feature, and m and b are basically the model parameters. So here in this case, depending on the different values of m and b, okay, different values, depending on these different values of m and b, we have multiple such lines. We can draw multiple such lines or possible regression lines which can pass through the points. Okay, and depending on the actual and the predicted values, we need to find out their cost functions. We need to find out the loss, average loss for all these all these lines. Okay, so here in this case, we need to find out the value of parameters b and m corresponding to which straight lines fit based to the data. Okay, so again, it is depending on the the position of this line. The position of this line is actually depending on the two parameters, that is b and m. So here in this case, here in linear regression, since we know that there are only two parameters based on which the regression line depends, the position of the regression line depends. So here in this case, we need to optimize our optimization problems. Problem here is basically the objective of our optimization problem in linear regression model is basically to optimize the value of b and m to minimize the cost function. Okay, so we just now we have seen that what is an error. So error is basically the difference between the actual minus predicted, the difference between actual and the predicted value. Okay, so in the cost function in general is basically it measures how a machine learning model performs. So it also, this cost function helps it also helps to define, or it also helps to measure the performance of any model. So the cost function is a calculation of error between the predicted and the actual, and which is represented by a single real number. So in general, this cost function j can be given as, like, for linear regression, we usually give it as the difference of the difference between this actual and predicted square of this. We take the average square. Okay, so when we put this y hat, that is the predicted value, equals to b plus mx in the above equation. Okay, so let's put this value. So we get something like this. So here in this case, like, j gives you the it gives us the cost function. So therefore, the best fitting model would be the one which minimizes the value of the cost function. Okay, so we have to minimize this cost function. So the question arises, how to minimize the cost function. Okay, how to minimize it? So we have to establish the fact that all the straight lines are just different combinations of the model parameters. So here in this case, the model parameters are b and m. B is nothing but the y-intercept of the regression line, and m is basically the slope of the line. So for different lines, we can have different slope values and different y-intercepts. Okay, so the cost function is the function parameters. The cost function is the function of parameters b and m. Okay, so therefore, by changing the values of b and m, we can change the cost function. Okay, that means for different values of b and m, obviously the cost function would be different. So when you put different values of b and m over here, you may get different values of cost functions. Okay, we will keep changing the values of b and m till we find the combination where the cost function is minimized. Okay, so that means we have to grow gradually. We have to change the value of b and m gradually, so that this combination will generate the minimum cost function value. Okay, to find the best combination, we basically use the gradient descent algorithm. Okay, so it is one of the optimization technique where we use this gradient descent algorithm. So the gradient descent in basically gradient descent algorithm is a optimization algorithm used to minimize the cost function by iteratively updating the model parameters in the direction of the steepest decrease of the loss. That means if a loss is getting decreased, then we have to gradually change the parameters value in the same direction. And how to decide that direction, that is basically decided by this gradient descent. So here the objective of objective is basically given a loss function j theta. So in this case, this theta is nothing but the model parameters. So for our case, for linear regression, the theta is basically b and m, and we want to find out the parameters theta such that it will minimize this j of theta. Okay, so the idea is compute the gradient partial derivative of loss function with respect to either b or with respect to m. Okay, we have to find out the partial derivatives of the loss function, and we have to move the parameters opposite to the gradient direction. Okay, so we have to move our parameters opposite to that direction, and we have to repeat this process until we find out the minimum cost function, until we converge, until it get converge. Okay, so, like there are different optimization functions, optimization algorithms. One of them is basically the gradient descent. Again, as we have seen, cost and loss nomenclature. So, in a same way, we have the gradient descent and stochastic gradient descent or minimized gradient descent, depending on the samples that we use, basically. So the first is basically gradient descent, which is basically also considered as a batch gradient descent. So it updates the parameter using the full data set. So when we use the entire data set, when we perform this optimization, when we use the entire data set to find out the parameters, to find out those parameters, then that becomes a gradient descent algorithm. So here in this case, this theta equals to theta minus eta change in j of theta. Okay, so this eta is basically nothing but your learning rate. Okay, so this can also be denoted by alpha. Okay, so this is your learning rate, and we are actually changing the value of theta. We are getting the different values of theta. Okay, second one is a stochastic gradient descent, that is SGD. It updates the updates parameters using one sample at a time. Okay, so if we when we consider one sample at a time, then that becomes your when we consider one sample at a time to calculate the optimized value, to calculate the best parameters, the best values for the parameter, then that becomes your stochastic gradient descent. Then basically the third one is nothing but the combination of these two, that is mini batch gradient descent. Okay, so this mini batch gradient descent uses small batches, most common in deep learning. So this theta is basically theta minus this eta and change in the cost function for a batch. That batch can be let's say the batch can be 30, a batch of 30 samples are taking together, batch of 100 samples are taking together. So that is again a hyperparameter, I mean to say. So like the best trade-off between the speed and stability, we have to decide, like based on this we decide the size of the batch. Okay, so there is no fixed value or a standard value of batch that one should consider, but the thing here that we need to understand is whether our model is getting learned out of the given batch. Okay, so that is actually is required, okay, while choosing or while applying this gradient based optimization. Okay, so let's first discuss this gradient descent, the very first the algorithm, that is when we apply entire data set, when we use entire data set to find out the best parameters. Okay, so there are few steps that we need to follow, that we need to follow while implementing this algorithm. The first is basically initialize the parameters randomly. Okay, so at the very first, actually we need to randomly choose the parameters. Okay, so as we have seen in the previous slide, that least square linear regression method can be used in a linear regression analysis to get the value of m and b. So basically in that, actually in least square regression method, the random values are basically nothing but the average of all the values. Okay, so in some cases you see that this can be the average, this can be average. Okay, this can be average, or this gradient descent algorithm tells me that this can be chosen the random value. We have to generate the random values. Okay, so it depends on which particular method we use actually. We use based on that we need to choose the value of m and b. Okay, so here actually we are broadly considering that it should be a random value. Okay, then the next thing is compute the predictions. Then using this m and b values, put this m and b values into the regression line equation, that is y is equals to mx plus b. Okay, and then these values into that equation, and then what we have to do for all the samples, since this is a gradient descent algorithm, so in gradient descent we are considering all the samples. So since we are considering all these samples, so what we have to do, we have to compute all we have to predict the y hat, we have to predict the values for all corresponding x values. Okay, and then depending on the different y hat values, depending on these different y hat values, we have to find out the loss. Okay, so this loss is nothing but basically a cost. Okay, cost, because this is basically nothing but the average loss across all predictions, average loss across all predictions. Okay, so this is basically a average loss. Okay, something like this. And then we have to compute the gradient. So how we can compute the gradient, that we will see. So this gradient is nothing but the partial differentiation with respect to the parameter b or with parameter m. Okay, so we even can choose the parameter m or we can choose the parameter b, and then with respect to these parameters we have to take the differentiation. Okay, we have to take the change in the value of loss. So this would be something like this. So here in this case, if I have this loss is like I'm considering this loss by L, and I have on x-axis I have the parameter m, and on y-axis I have the parameter b. Okay, so when I draw it for different values, when I draw it for different values of m and b and L, then I may see some graph like this, something like this. I can observe something like this. Okay, so here in this case, this is basically a global minimum value with respect to this particular m value and this particular b value. Okay, so for this particular m and b value, for this value and for this value, I may observe the minimum loss function. However, for other values, this is basically this would be the loss function. For other values, the values for the other m and b values, I may observe the higher loss. Okay, so gradually what I have to do, computing gradient means gradually I have to change in the y, like change in y with respect, change in this loss function with respect to either change in m or change in b. Okay, so when I take it like here in this case, the parameters are, since the parameters and m as parameters are m and b, here in this case the parameters are basically m and b. So I am not taking the complete derivative. I'm not taking the change in L with respect to this B and M. Okay, I may consider it with respect to either B or either M. So that's why we consider it as a partial derivative with respect to either M or with respect to either B. Okay, so that gives me the delta M or delta B. Okay, and then what I will do, I will update the parameters. The next step is to update these parameters. So initially let's say that I am using m equals to 2. I'm assuming that m equals to 2 and b is some random value 0.4. Okay, now this change in m and change in b will give me the updated value of m and updated value of b. Okay, so at a time I can get the updated value of m, and the other value can be calculated by putting the equation, by putting this value of m into the equation y is equals to mx plus b. Okay, so what we have to do, we have to repeat this, until the loss converges. That means until we reach to this global minimum. Okay, so from this point again, when you calculate the loss is getting increased. So in this direction, the loss is getting increased. Okay, or the other stopping criteria could be this maximum iterations. So the other stopping criteria can be this maximum number of iterations. So let's say that I'm not looking for the global minimum. Even if I reach to this particular point, then also I feel that it is okay. But by this time I may reach to some 100 iterations, which is the stopping criteria here in my case. Okay, so and like, since this is a gradient descent, that means we are using the entire data set. So the issues or the trade-off is actually depending on the resources that we are consuming. Okay, so that means for the larger size of the data set, obviously I have to fix the maximum iterations. I will not always look for the global minimum value. Okay, so these are basically the steps actually in gradient descent. When we start actually doing the things, we have to initialize the parameters randomly. The other method, as I said earlier, that if we don't want to randomly choose, we can take the average of all x bar and y bar. So we can take the average of all x and y bar, and then we will pass the line. Okay, we will pass the line through that point. Okay, and for that particular line, then we calculate this m and b. Okay, so b is basically your y-intercept and m is basically the slope of this line. Okay, so this line will pass through x bar and y bar. So this is basically with the help of least square linear regression model. However, for other case, you can choose the random value of m and b. Then we compute the predictions, then we calculate the loss with respect to those predictions, and then we compute the gradient. Gradient is nothing but the partial derivative with respect to this m and b. Since here in this case, here in the linear regression model, since we are talking the linear regression model, there are only two parameters. Okay, so when we talk multiple regression or multiple linear regression, in that case we may have multiple m values, m1 m2, this is m1 m2 m3 likewise. So it depends on the number of independent variables. So this m1 is basically with respect to the first independent variable, this m2 is with respect to the second independent variable, this m3 could be with respect to the third independent variable. Okay, so likewise even for this depending on the type of linear regression, depending on the regression analysis, we have this values. Okay, and then next we update the parameters, and then we have to repeat it until it get converged to the minimum value, global minimum value, or we reach to the maximum number of iterations. Okay, okay. So let's say that we are plotting this j. J is nothing but your cost function, as we have discussed over here. This is a loss. Okay. So j is a cost function, and a is nothing but a parameter. So a is any random parameter for this j. So j of theta. So here in this case, this theta is nothing but your a. The parameter is a. Okay. So let's say that we are at this point. So we have chosen the random value of a. The random value of a is a1. For this a1, I'm putting the value of a1 into the function f. So I got this particular value. Okay, so at a1, the error is this, or the cost of the my function would be this one. Okay, so what next, what I have to do next? Okay, so the next value, I have to reach to this point. Okay, I have to reach to this point. So we are at this point right now, we are at this point with the help of this a1, and when I'm putting this a1 into this function, I'm getting some value. Okay, and that value gives me the cost, this one. So we want to reach here, we want to know for what value of a or j equals to f of a will assume minimum value. Okay, so in LR we assume that this f is nothing but your MSE, mean squared error. We are assuming that it is nothing but your MSE. Okay, so here in this case, for which value of A, so for which value of A, the cost would be minimum value. Okay, the cost will be generated as the minimum value. Okay, so we want to find out this A value. Okay, so let's, what we will do, as given in these steps, we have to compute the gradients. Okay, so what we will do, for each value of A, for each value of A, we will calculate the slope at the point. Okay, so here actually I will we will calculate the slope at the point. So it is basically dj by dA, derivative of this cost with respect to A at A1. Okay, that gives me the f dash A1. So then we will move one step ahead. We will move the step alpha in the direction to reach A1 minus alpha into f dash of A1. So what I will do, I will then calculate this value. I will update. I will, this A would be a learning rate. Here in this case, A would be the learning rate, and it is recommended to have the small fixed quantity in the range of 0.01. Okay, so we'll use this we'll use this alpha as a learning rate, and then we'll again see whether I am reaching towards this direction for in the global minimum, or I am reaching towards the maximum value. Okay, so if using this equation, using this alpha, if I am actually reaching to the opposite direction, then we'll have to change the value. Then we'll have to change the value. And if I'm reaching towards the global minimum, then again I will calculate the value of, again I will calculate this delta A1, so that this change in A1 will cause to minimize the cost function. And so therefore the size of our steps is depending on the slope f dash A. So here in this case actually, I will, next point that I will reach to would be this one. I have to reach to this particular point. Okay, so higher the value of slope which occurs may from minima, larger the steps, and vice versa. So here in this case, alpha is a small fixed quantity. Okay, so therefore the size of steps is dependent on the slope alpha f dash A1. So what I have to do, I have to gradually, from this point, I have to gradually how to move to this particular point. Okay, so if I keep the fixed value of alpha, if I keep the fixed value of alpha, that is, as we move closer to the minimum, the slope decreases, and hence our steps towards minimum keeps getting smaller. Okay, so let's say that I am, instead of this, if I am using the fixed value of alpha, so I will start from here, then I will reach over here again. From here I will reach over here, then again from here somewhere I will reach over here, not this point, not this point, which is basically a global minimum. From here again I will reach over here. Here actually I am growing in the negative direction, that means the cost is getting increased. So again I will come back here, again I will go over here. So I may not reach to this global minimum if I use the fixed value of alpha. So that's why in the further steps you see that the difference is getting small. When you reach to this particular global minimum, the difference is actually the zero. Okay, so that's why the slope becomes zero. So at the minimum this slope would be zero. Okay, so this is like this is how that we actually calculate the gradient descent. So in general, like to summarize this, the gradient descent in LR, these iterations of the gradient descent algorithm can run multiple times depending on the nature of function and the alpha, that is learning rate. And of course, where we start from, that is the random value that we choose. So the random value basically decides or will help us to check whether this random value decides how many iterations may be required. So if we can work on deciding random variables, if we can minimize the actually if we can predict a closer value of A1, a closer value of A, then it will also help us to minimize these steps. Okay, then same methodology can be used to minimize the cost function j, which is a function of model parameters b and m. So here in this case, actually, we instead of uh, uh, like point, like instead of representing this particular like graph in terms of a, we can do it with respect to b or with respect to m. Okay, so changing them through iterations of the gradient algorithm. So this is how like the gradient algorithm can be applied. Okay, so far, do you have any questions? I'm actually ready to take few questions.
Sir, am I audible?
Yes, sir. Yes, sir.
Sir, what if the loss surface has multiple peaks and valleys? That-
Okay. If sir, okay. So, sir, actually, for that reason, we actually need to, if there are multiple peaks and valleys, so in that case, we need to change the learning rate, sir. So, in that case, probably we have to reach to the global minimum, and since the loss function is basically for linear regression model, for higher values of loss, like if the error is high, then obviously this MSE performs well. So we may have to change the loss function in that case. So to reach the global minimum value, the very first thing that we need to do is to take the small steps, that is the learning rate. And if it is not suitable with respect to our data set, then we may have to change the loss function.
Okay. So, sir, suppose I have some value, I have chosen some value of learning rate alpha, and
Mhm.
my model gets stuck somewhere in the, not in the global minimum, but at local minimum, some local minimum.
Mhm.
Then only the best way is to change the algorithm to so that it tries and finds the global minima, or is there some other way for that?
No, sir. Global minima is basically obviously like we have to take the different value, different combinations of the learning rate. Like
Okay.
the learning rate will help us to get out of that global minimum.
Okay. Okay. Got it. Thank you, sir.
Yeah, welcome. I can see that your question was there on the multiple values. Okay. Okay. Any more questions?
Sir, one last one, maybe.
Yes. Yes.
Um,
Please.
when the algorithm starts, how does it see the loss surface initially, full loss surface initially, or it generates when each step is calculated every time?
Sir, it actually sees when we calculate, when we like after getting like after calculating each step, it will get to see the loss function. So actually, what we tries to do with respect to the previous step, whether we are reaching towards the minimum or maximum, that we are taking into consideration. So let's say that if we are like we have calculated and we are actually moving towards the minimum value, that means the in the previous iteration, say the value is for the cost function, the value is 2, and in the next iteration with some updates the value is 1. That means we are reaching towards the 0. So here in this case, that will allows us to check or to determine whether we are reaching into the correct direction or not. So let's say if we are getting some value as 3 or 4 after updating the values, after updating the alpha and other parameter values, then we may have to change the directions in that case.
Okay. Okay. So as I understand, loss surface is generated only once we our algorithm goes fully through all the points.
Yes, yes, yes.
Okay. Thank you, sir.
Okay. So, any more questions? If there are any questions, then we can take it. Otherwise, actually, I wanted to take one hands-on actually, but some work has come to me, so I will share the file with the organizers, and so that you can actually work on that file. So probably through that, that is nothing but a collab notebook on a simple linear regression model, where you can see by changing the values of m and b, you can see actually how the loss function, how the value of the cost function is getting changed. That is basically a simple implementation of a gradient descent model on a small size of data set. So I will share it with the organizers so that they can share it with every participants. So yeah, that's it from my side for now.